In this training video, we continue from our previous study and continue looking at the extended link ratio family. And the equation that we looked at in the last video, in particular, was the Murphy method, in which we add an intercept term into the Mach method. So the Mach equations, we're just looking at bx plus an error term, so no intercept, and Murphy added this intercept term here. Now another way of formulating this equation is actually to subtract x off both sides. So x is the current cumulative, and y is the next one. If we subtract x off both sides, we end up with the incremental. Okay, and if we do that, we just end up with this b minus 1 term. Now this equation is actually a more useful formulation of it, as we are able to test whether the ratios are in fact contributing to the projections. If this term b minus 1 goes to 0, then we know that the ratio isn't actually helping us estimate the incremental, which is the part that we're interested in, because we already know the current cumulative. In which case, the best estimate of the incremental term, the component we're interested in, is in fact the average of the incrementals going down. So that would, in which case, we don't actually need our link ratios because they're not adding any information into our projection. Okay. So what we're saying here graphically is that we've got an insert term here, and around that, those incrementals are scattered randomly. We're not actually needing the link ratios. Okay, if we go back to the Mach data now. So open the database workbook 104A if you don't have it open already. The open database icon, workbook 104A, open. Start typing in Mach, so MA will take us to the triangle group starting with MA. Just scroll down a bit and then select Mach. Double click to open it. Select the cumulative dataset, ILC. ELRF to open ELRF, so the ELRF tab at the top here. And we're going to load the Murphy method. So go to Model Templates, pink M's with the upward arrow, and select both. You see intercept and ratios. That's the Murphy method with delta 1. Okay. And what you see in this table, there's a whole lot of pink numbers, which indicates insignificant parameters. Now, if we look at the ratios minus 1, our ratios minus 1 are not significant. If we optimize, click on the O, optimize, we find that all the ratios go to 1, so the ratio minus 1 goes to 0, which means that our previous cumulative is not used in projecting the next incremental. What we find is we take the average of the incrementals going down the triangle, and we use that estimate as our projection for the other incrementals. The only time we use ratios are in the last two development periods where we don't actually have enough points to estimate multiple parameters anyway. Okay. If we load the Cape Cod model, go back to Model Templates. Cape Cod, it says use intercepts, do not use the ratios. So effectively it's going to be the same model that we started with the Murphy method and then optimized. So if we do that, find that instead of using the ratios here, we just use those estimates of the average incremental. But essentially it's going to be the same model. Let's do some revision here. So we'll go back to our PowerPoint slide. Okay. Let's take some cumulative data, we'll put it in this triangle here, and adjust it by some favorite exposure base, which will turn E1 to ES. Okay. And we create the incrementals along here. So we adjust it, create the incrementals. If we take the accident years as labeled here, and for instance this could be 1990, 91, 92, labeled at W. If we graph the incrementals against these W and see no correlation, that is, there's no pattern here, it's just random scatter around an average incremental, A, then we would find that there is no correlation between the cumulative at J and the cumulative at j minus 1, which is your y and x respectively. Alright, in that case, you would find that your b minus 1 in this equation, because you're using alpha, is equal to 0. Alright, so under condition 1, you would abandon your link ratios and projection and simply use the average incremental as your best estimate for the remaining portion of the triangle. On the other hand, if you find that there is a constant trend again when you plot these incrementals against the accident period, so you've observed this, then you're likely to see that the link ratios do have predictive power. That is, if you use this, then say b is greater than 1. So in other words, you've got some predictive power in your ratios, in which case you would use them for projection. But if we go on to the next slide, if we actually add a parameter to estimate this trend now, which we can do here with this A1W, that's our trend parameter, okay, with an intercept in the ratio minus 1, more often than not, you would find that your b minus 1 in this equation also goes to 0. Okay, sometimes you need both the trend and the link ratio, and sometimes you need just the link ratio, but more often than not you find that this component has more predictive power than that one, and you find that you don't actually need the link ratio. Alright, let's see what happens in the MAC data, so the MAC triangle group. So let's load now the model that estimates everything. So go back to model templates, click trend and ratio, intercept, yes, trend, yes, ratio, yes, with delta equal to 1. Okay, so we're estimating all the equations here. And you can see that we've got a lot of numbers, colors in this table. If we optimize twice, it's going to remove the unnecessary parameters that we don't need. Let's do that now. So optimize, and again. And what we find is that, as before, the link ratios aren't actually used except in the last two development periods. We have the intercepts are used in all periods except the last two, where we don't have enough points. And we also have this trend parameter going down development periods 1 and 2. If we look at the residuals now, we find that they're, we don't observe any particular pattern in them, which is good. We've captured the structure in the data, but as we'll describe, we don't actually know how to allocate that structure fully. But at least in terms of the method, we can say that it's representative, at least, or more representative of the data. Okay, let's go back to the MAC method for a second. So go back to model templates, load the MAC method, that's ratio only, y, delta 1, okay, and forecast from this method. So click on the green triangle, yellow downward arrow, forecast. Now the forecast table, as we might have discussed in previous videos, you've got the black numbers are from the fitted models with your method, or your projected if you're looking at future cells. Your blue numbers are your observed, and your red numbers are your standard deviations. So you should be able to easily produce the black and blue numbers. The standard deviations might require a bit more calculations. Now, if we go to the forecast summary table, forecast summary, FS, in red, click on that. If we look at the CVs going down the accident year, you can see we've got all these different tabs to look at. We've got breakdowns by accident year, calendar year, percentage differences, etc. If you come back to this tab, accident years, if you look at the CVs going down, you can see that particularly in the last 4 years, these CVs are actually increasing. Well, this is actually the opposite of what we expect, because when we're projecting more numbers on the accident year, so we're projecting more numbers here, we actually expect the CV to go down, because the more numbers we're projecting, the lower the CV is. Okay, so the MAC method, if we come back to the forecast summary, FS, is not giving us this information. The CVs are actually increasing. And the reason for that is that we've already seen this method is actually not the best method for fitting this data. It is deficient. It doesn't include all the structure in the data, and the Cape Cod model is better, and we would expect that the CVs would behave more reasonably if we fit that model. So let's do that now. Go back to model templates. Go on Cape Cod. So intercept only, no ratios. Okay. Forecast. Go back to the forecast summary. So forecast green triangle, yellow downward arrow, forecast summary, red FS. We see that the CVs are behaving much more reasonably, so they're not increasing in the same way that the MAC method was. Let's now take a look at the logbook. LOG in blue with click on that, and we can see that the summary statistics are better for the Cape Cod as we expect. The BIC is lower, for instance. Normality is a bit better. And we can see that the difference in the forecast scenarios as well that we're projecting. So this is from the MAC method. Okay. And then most recent run 9, is from the Cape Cod method. And you can see the projections that we have there. Okay. We're now going to conclude with a brief discussion of the conditions that we find. So, condition 1, I'll just go back to the slide. And wait a moment. Condition 1 and condition 2, most data sets don't actually satisfy those conditions. Okay, but there is a third condition, as you probably saw briefly when I was flicking through the slides, that we more commonly encounter with real data. And that is where your trend going down the accident years for a particular development period isn't actually constant. So condition 2, if we're looking at it, we've got this constant trend, alright? Constant trend. What we more often see is condition 3 where this trend isn't actually constant. So we're looking at something that might look, say, like this. Okay? What we find under conditions 1, 2, and 3 is that link ratios sometimes capture some of the trends. Okay, emphasis on the sometimes capture some. But you don't actually have any idea of how much of those trends they're capturing or what they're actually capturing at all. And residuals, so in other words the error terms, the difference between the trends in the data and the trends in the method only give us some idea of the relativities. They don't actually give us a magnitude. And these non-constant, any method which does not directly measure or adjust for these non-constant trends, all right? So if we don't actually know what these trends are or how we're adjusting for them, this is T1, this is T2. So any method that doesn't adjust for these will, by definition, contain some structure in the residuals. Okay, so remember, the structure in the residuals is not something that we want to see because it means that our method isn't fully describing the data. And this will mean that our projections from that method will also be deficient in some way. So because we're not capturing the full structure in the data, we're not capturing the full structure when we do our projections, and our projections will be deficient. And that applies to whether we're projecting payments, whether we're projecting counts, whether we're projecting incurred costs, or any other type of loss development array. Now, how to handle condition 3 more naturally is discussed in much more detail in the video introducing the Probabilistic Trend Family modeling framework. And the reason that this Trend Family modeling framework was actually developed was to handle condition 3 that we observe in real data, and also to formulate the analysis in a more intuitive way where we're actually dealing with trends, given that trends are what we're actually interested in. Well, that concludes our sequence of videos on the link ratio techniques module and the extended link ratio family. Thank you.